In modern data science, there is a mathematical tool built specifically to estimate histories that never actually occurred. When a policy is passed or a conflict breaks out, researchers use this tool to reconstruct the exact path a society would have taken if that event had never happened. The method became famous when economists used it to calculate the true cost of the conflict in the Basque Country. They wanted to know what the region's economy would look like in a peaceful timeline. To do that, they used what's called a synthetic control method. This chart shows exactly how the method works. The algorithm creates a synthetic version of the Basque Country by taking a mathematical average of real, observed economies that remained peaceful. These peaceful comparison regions are called the donor pool. They blend together to form the dotted line, which becomes our hypothetical peaceful future. The massive appeal of this approach is its transparency. You can see the weights, you can name the regions, and the resulting prediction is built entirely from a neat, contained menu of real historical cases. Analysts treat this donor pool as an objective catalog of historical possibilities. But look closely at what the algorithm is actually doing. We are trying to estimate an unobserved, unrealized history, yet the method restricts itself exclusively to the trajectories of states that history actually realized. If the menu of available donors is heavily curated by historical forces before the data scientist even downloads the spreadsheet, then our mathematical predictions of what could have happened are skewed from the start. To understand why this is a problem, we have to look at how countries end up in comparative data sets in the first place. Researchers David Waldner and Benjamin Smith point out a quiet reality in political science. A country only gets a row in a dataset if it survived history long enough to become a recognized sovereign state. Take the Arabian Peninsula. Studies often analyze whether resource wealth harms state development. But the sovereign states on the peninsula exist today specifically because their resource wealth helped them survive colonial partition. Their survival is entangled with the exact variable analysts are trying to study. In statistics, this is a form of collider bias. Sovereignty is not a neutral precondition for having data. It is an outcome heavily shaped by external forces. By only analyzing the entities that exist to be counted, the dataset inherently links survival to the variables being studied, skewing the math. History deletes its losers. Standard datasets do not represent a complete spectrum of historical possibilities. They are catalogs of survivors. This exact dynamic breaks the synthetic control method. To be considered a usable donor in the algorithm, a state or economy must possess a clean, continuous, and unbroken data trajectory across the entire observation window. Think about who gets excluded by that rule. States that collapsed, regions that violently fragmented, or economies that hyperinflated into ruin, like the Soviet Union or Yugoslavia. Because their data is erratic or discontinuous, analysts throw them out. We can visualize this as a massive historical funnel. A huge universe of possible histories is squeezed down into a smaller set of realized histories. Then, the analyst filters them again, catching the broken and plunging lines, and allowing only the smooth, stable survivors to pass through into the donor pool. Once the survivors are in the bucket, the algorithm draws a strict geometric boundary around them, called the convex hull. Every prediction the method makes about the hypothetical future must live entirely inside this illuminated box. This reveals a major geographic flaw in the math. Because the disaster trajectories were systematically filtered out of the donor pool, the entire convex hull is displaced. It floats comfortably in the safe, benign region of the data space, far away from the crisis zone. By insisting on clean, comparable data, analysts erase the exact paths of crisis and disaster that a region might have actually fallen into if they hadn't intervened. When confronted with this, a data scientist will usually point to their primary defense metric, the perfect pre-treatment fit. They will confidently show you that their synthetic model traces the target's past flawlessly. This graph illustrates that illusion of security. The solid real-world line and the dotted synthetic line lock together before the treatment event occurs. Matching the past perfectly gives analysts massive confidence in their projection. But there is a concept from signal processing called historical aliasing. A decade of rising output could be a credit bubble or a demographic boom. They look mathematically identical, right up until the moment they fracture. Distinct historical mechanisms can share the exact same past, while implying sharply different futures. The algorithm has no way to tell the difference. A perfect statistical fit only proves that the model successfully matched the trajectories of historical survivors. It remains totally blind to whether those survivors actually represent the target's unlived possibilities. Synthetic control tricks us into answering a conditional question. What would have happened to this region, assuming it survived? When the question we actually need to answer is unconditional. What would have happened? Every time a researcher publishes a synthetic counterfactual, they are actually relying on a massive, unstated philosophical premise. They are assuming that historical survivors adequately represent all historical possibilities. This requires a shift in how we handle data. Analysts can no longer treat their donor pools as neutral givens provided by a spreadsheet. They have to actively defend their survivorship assumption, case by case. Moving forward, statistical models must be built to account for empty spaces, designing bounds that calculate the impact of failed trajectories and missing data. The math can only calculate the numbers we feed into it. To accurately predict the histories that never happened, modern data science must fully reckon with the histories that failed.